Hi, in this lecture we will plot the Bode plots for some more functions. Say h of s equal to 1 by 1 plus s by p, okay, where p is pole. Okay. Substitute s equal to j omega. H of j omega is equal to 1 by 1 plus j omega by p. The magnitude is 1 by square root of 1 plus omega by p whole square, and the phase is minus tan inverse of omega by p. If you take any complex number a plus jb, its magnitude is given by square root of a square plus b square, and the phase is tan inverse of b by a. So magnitude in dB is equal to 20 log 1 by square root of 1 plus omega by p whole square. This can be written as minus 10 log 1 plus omega by p whole square. Here two cases. If omega is less than p, then the magnitude becomes minus 10 log 1 plus 0, because if omega is less than p, I can assume that omega by p is negligible term compared to 1. So this becomes minus 10 log 1, nothing but 0 dB. And if omega is greater than p, then magnitude is minus 10 log omega by p whole square. In this case, if omega is greater than p, omega by p whole square is much greater than 1. So I am neglecting 1. So this can be written as minus 20 log omega by p. So I will plot magnitude and phase plots here. X-axis omega, y-axis is magnitude in dB. Okay, so if omega is p, now I am rewriting the equations. If omega is less than p, then magnitude is 0 dB. If omega is greater than p, then magnitude is minus 20 log omega by p, and phase is minus tan inverse of omega by p. For different values of omega, we will plot the magnitude and the phase. Say if omega is 0.1 times of pole, okay, then magnitude is 0 dB as per equation number 1, and phase is minus tan inverse of 0.1. Okay. So this is approximately minus 5 degrees. Say. Now omega equal to p, then the magnitude is approximately 0 dB if I use equation number 2, and the phase is minus tan inverse of 1, so it is minus 45 degrees. if I take frequency of 10p, then as per equation 2, the magnitude is minus 20 dB and the phase is minus tan inverse of 10. So it is approximately minus 90 degrees. Okay. So with these values, this is 0.1p and this is 10p. So the magnitude plot is like this, where at the frequency of 10p, the magnitude is minus 20 dB per decade, and the phase plot omega. So here at p, the phase is minus 45 degrees. At 10p, the phase is reaching approximately minus 90 degrees, and at 0.1p, the phase is minus 5 degrees. So the phase function is like this. If you see this magnitude plot and phase plot, this magnitude is decreasing only after omega equal to p. For omega less than p, the magnitude is 0 dB. But if you see the phase plot, I'll change the pen color. If you see the phase plot, for omega less than p, the phase is changing. Okay, so the magnitude plot will not change till pole, but the phase plot or the phase plot will change much before the pole. This is one observation. And coming to the slope of this magnitude curve at p, the magnitude is 0 dB. At 10p, the magnitude is minus 20 dB. So from p to 10p, the magnitude is changed by minus 20 dB. So if frequency changes by decade, a factor of decade, then the magnitude is getting decreased by minus 20 dB. So the slope of this curve is minus 20 dB per decade. Similarly, if I take one more transfer function, h of s equal to 1 plus s by 0. Substitute s equal to j omega and do the same analysis what we have done for the previous examples. Then the magnitude curve, this is omega axis, this is magnitude in dB, this is z. Okay, so here we will get, I will change the pen color, this is omega, this is phase. The magnitude plot will be like this. This slope is 20 dB per decade and the phase plot is like this. This is 90 degrees and this is 45 degrees. It's 0. This is 10 times 0. Okay. Now we will summarize what we have learned so far. Just we will observe the slopes of magnitude plots 1 by s. What is the slope with which it is decreasing? Minus 20 dB per decade. 1 by s square. Slope is minus 40 dB per decade. Similarly, if I generalize 1 by s power n, the slope will be minus 20n dB per decade. Okay. Again, if you take h of s as s, then the slope is 20 dB plus 20 dB per decade, s square plus 40 dB per decade, and s power n 20 n dB per decade. Okay, next 1 by 1 plus s by p. For this one, the slope after omega greater than p is minus 20 dB per decade. Okay, and similarly if I take a transfer function 1 by s plus z, for omega greater than 0 z, the slope is plus 20 dB per decade. These are our common observations. If I take h of s as k, for example, its slope is 0 dB per decade because its magnitude plot is constant for all frequencies. With this information, we will try to plot Bode plots for little complex transfer functions. S by 2 into 1 plus s by 40. So now first step is identify the corner frequencies. Corner frequencies are nothing but poles and zeros. In this case, we don't have any zeros. We have only poles. What are those poles? Poles are s equal to 2 and 40. I am not taking minus sign because we are taking only omega here. So first you mark them as 240. Okay, so what is this one? 2 is pole, 40 is also a pole. Okay, so is there any s term or 1 by s term here? No. So before 2 the slope is 0 dB per decade. When you see a pole, then the slope decreases by 20 dB, or you just add minus 20 dB per decade slope to its previous slope. Its previous slope is 0, so here minus 20 dB per decade. Again you are getting a pole at 40 frequency. At 40 you are getting a pole, so whenever you see a pole, add minus 20 dB slope to its previous slope. So its previous slope is already minus 20, so minus 20 minus 20, it becomes minus 40 dB per decade. Now plot the magnitude plot. Okay, so here locate the corner frequencies. This is 20, this is 40. Okay, now before 20, what is the slope? 0 dB. The slope is 0 dB. So this is 0 dB. Okay, now after frequency of 2, what is the slope? Minus 20 dB. So this is minus 20 dB per decade. After 40 dB, what is the slope? Slope is minus 40 dB per decade. Okay, so if the transfer function, the same transfer function, if this transfer function is changed like this, instead of 1, if I write 10 by 1 plus s by 2 into 1 plus s by 40. So what is the modification that we can do? Here just you shift this plot up by how much, sir? Here the value of k is 10. This is 10. So 20 log 10 is nothing but 20 dB. So you shift this complete plot up by 20 dB. Then the curve will be like this. Like this. Okay. So this is 20 dB in the 2 frequency for 40 frequency. Okay, sir. Thank you.